In this section, I'm going to be discussing independent and dependent variable transformations. These types of transformations show up quite pervasively in a lot of the mathematics associated with signals and systems, so these types of transformations are quite important. To begin with, I'm going to discuss transformations of the independent variable, and the first type of independent variable transformation that I'd like to introduce is what's known as time shifting or translation. And what this does is it maps a function x to a function y according to a relationship that looks like this, where the constant b is a real number. So effectively what we're doing is in the expression for the function, we're taking everywhere that the independent variable t appears and we're replacing it by t minus a constant, where the constant is denoted by b. And this type of transformation has the effect of shifting the function either to the left or right along the time axis, in other words the horizontal axis of the graph. In the case that b is positive, y will be shifted to the right by absolute value b units relative to x. In other words, the graph is effectively delayed in time. On the other hand, if b is negative, y will be shifted to the left by absolute value b units relative to x. In other words, it's advanced in time. So at this point, I just want to consider a couple of examples to illustrate this transformation called time shifting, or equivalently translation. So suppose that we have a function x which looks like what's shown in this graph at the top of the slide. And suppose that we take our independent variable t in the formula for this graph that we have plotted, and we replace all the t's by t minus 1. This would correspond to a time shifting transformation where the time shifting constant is 1. Remember that we're replacing t by t minus something in the case of a time shifting transformation. So the thing that we're subtracting here is 1, therefore we're shifting by a value of 1. Since 1 is positive, we're shifting in the positive direction, in other words in the rightward direction. So the relationship between this graph here, this time shifted version of our original function, and the original function x is that this graph is shifted 1 unit to the right relative to our original graph. Then if we consider this other figure in the bottom right, so here we have x of t plus 1 graphed. So in other words, we've taken all of the t's in this formula here for the graph that we have plotted, and we replace them by t plus 1. Now remember, with a time shifting transformation, we have to read the expression as t minus something. The constant that we're subtracting is the amount we're shifting by. So in this case, we have to read this as t minus, and then the value that we're subtracting is minus 1. So t minus minus 1. So the amount we're shifting by is minus 1, which is negative. So we're shifting in the negative direction, in other words, in the leftward direction. So the relationship between this graph here, our time transformed version of our original function, and the original function x, is that this graph is shifted 1 unit to the left relative to this graph. The next type of independent variable transformation that I need to introduce is what's known as time reversal or reflection. And what this does is it maps a function x to a function y as given by a relationship like what's shown here. And effectively what this is saying is that with a time reversal transformation, we're taking the independent variable, which in this case is t, and wherever it appears in our formula for x, we're replacing it by minus t. So we're changing all the t's into minus t's. And then the question becomes, well, what's the effect of this? What does this do to the graph of the function? Geometrically, the effect that this has is it flips the graph of the function from left to right. So if we have our original function x looking something like what's shown in the bottom left graph here, if we apply a time reversal transformation to it, in other words we plot x of minus t, the graph that we get looks like what's shown in the bottom right. And you'll see that the relationship between these two graphs is effectively they've been flipped sort of left to right. In other words, mirrored through the vertical axis. So the portion of the graph that was originally on the negative part of the t-axis is now flipped around and it's on the positive part of the t-axis. And the part of the graph of the function that was originally on the positive part of the t-axis is now flipped around and it's on the negative part of the t-axis. Or another way to look at it is you're sort of playing the function backwards. Instead of graphing it from left to right, you're graphing it from right to left. The next type of independent variable transformation that I need to introduce is what's called time compression or expansion, sometimes also called dilation. And what this does is it maps a function x to a function y as given by a relationship like this. And effectively what this relationship is saying is that everywhere in our formula for the original function x, where we have our independent variable, which in this case is t, we're going to take that t and replace it by a constant a times t, where a is a strictly positive real number. In other words, a is a real number that's greater than 0. And we might wonder, what's the effect of such a transformation? What does it do to the graph of the function? And it turns out the effect that this type of transformation has is it either stretches the function horizontally or compresses it horizontally. In other words, compresses or expands it along the horizontal axis. In particular, if the constant a is greater than 1, the function y will be a compressed version of the function x, where it's compressed along the horizontal axis by a factor of a. And if a is less than 1, then y will be expanded, in other words, stretched along the horizontal axis by a factor of 1 over a relative to x. On this slide, I have an example to illustrate time compression and expansion transformations, or sometimes they're called dilation transformations. So at the top of the slide, I have a graph of a function called x, and what I have on the bottom half of the slide are two dilated versions of the original function. So if I look at the function in the bottom left of the slide, what I've done, the relationship between the graph in the bottom left of the slide and the graph at the top of the slide is effectively everywhere in the formula for the function that's plotted in the top of the slide, I've taken the independent variable t and replaced it by 2t. So this corresponds to a dilation type transformation. The question becomes, well, what effect does this have? What's the relationship between the original function x and this new version of the function x2t? As you can see here, the effect is that this graph here has been sort of squashed horizontally by a factor of 2. So for example, this function here is non-zero between -1 and +1, but after we apply this transformation here, the graph is now only non-zero between -1/2 and +1/2. In other words, the horizontal scale has been sort of squashed by a factor of 2. On the other hand, if we look at the graph in the bottom right, here what we've done, if we look at the relationship between this formula here and the original formula at the top of the slide, effectively what we've done is we've taken the independent variable in the formula for our original function, and everywhere that the independent variable t appears, we've replaced it by 1/2 times t, or equivalently t divided by 2. And you can see the effect that this has is it stretches the function out by a factor of 2. So again, if we look at the original graph, this function is non-zero between -1 and +1, whereas this graph here at the bottom right is non-zero between -2 and +2. In other words, the entire graph has been stretched by a factor of 2. The next type of independent variable transformation that I need to introduce is what's known as time scaling. So time scaling takes a function x and it maps it to a function y, as given by this equation here, where the constant a that appears in this equation is a non-zero real number. So in terms of what effect this has on the signal that's being transformed, it's essentially a combination of dilation and or time reversal. And you can sort of see that probably it's somehow going to be related to both dilation and time reversal. The reason why is if we choose a to be strictly greater than 0, then this equation here becomes the same as in the case of dilation, in other words, time compression and expansion. In the case that we choose the constant a to be -1, this equation becomes time reversal. So you might guess somehow that this transformation is somehow a combination of both of these things, and in fact it is. In particular, if the magnitude of a is greater than 1, then the function is compressed along the time axis by a factor of absolute value of a. If a is less than 1, the function is expanded or stretched along the time axis by a factor of magnitude 1 over a. If the magnitude of a is equal to 1, then the function is neither expanded or compressed. And then lastly, if a is negative, the function is also time reversed. So you essentially have a combination of expansion, compression, and or time reversal happening with this type of transformation. A few additional comments with respect to dilation and time reversal operations. An important thing to know about these two types of transformations is that dilation and time reversal operations commute. In other words, their order can be interchanged and it doesn't change the overall effect of the transformation that's being performed. This is important because some types of time transformations do not commute. The order matters. You can't interchange them without changing the overall effect of the transformations that are being applied. And as you can see above, time reversal is just a special case of the constant a in the equation up above being equal to -1, and compression and expansion is just a case of a being greater than 0 in the equation up above here. On this slide, I have an example illustrating time scaling transformations. So in the top left figure, we have a graph of a function called x, which is just chosen for illustrative purposes. And then we have 3 other graphs on this slide where we've plotted essentially 3 different time transformed versions of the original function x, where the particular time transformations that we're applying are time scaling type transformations. So in the figure in the top right of the slide, you can see from the expression that we have we've plotted here, it's x of 2t. So effectively what we've done is we've taken all of the t's that appear in the formula for the original function, x, that we were given, and we replaced them by 2t. And the effect this has is it compresses the graph along the horizontal axis by a factor of 2. Then in the bottom left, we have a figure where we have the x of t over 2 being plotted with respect to t. In other words, we've applied a time scaling operation to our original function x where the scaling factor is a half. The t has been multiplied by 1/2, or equivalently divided by 2. And the effect this has on the graph of the function is it stretches it horizontally by a factor of 2. So this graph here, compared to the one in the top that we started out with, it's been stretched by a factor of 2 in the horizontal direction. And then lastly here we have a time scaling operation where we've applied a scale factor of -1, which just corresponds to time reversal. So this function here is simply the original function x time reversed. The last type of independent variable transformation that I need to introduce is essentially a composition or combination of time scaling and time shifting. So with this particular type of transformation, it maps the function x to the function y, where the relationship between them is given by this equation here. So effectively what we're doing is we're taking the independent variable, which in this case is t, and we're replacing it by at minus b, where a and b are real numbers and a is not equal to 0. Now when we look at this, you might sort of guess that this is a combination, well, if I hadn't already told you, you might guess that this is a combination, in other words a composition of time scaling and time shifting. The reason why is we know from earlier that if you subtract a constant, this has the effect of applying a time shift, and if you multiply by a constant, this has the effect of doing a time scaling operation. So you might guess that this transformation is somehow a combination of time scaling and time shifting. And I said a moment ago this is what it is, so no surprise there. But that's sort of the logic behind how you could deduce that on your own. Now, one thing that causes particular problems often for students for this type of transformation is it involves 2 different types of transformations, time scaling and time shifting. And what's special about these types of transformations, these 2 types in particular, is they do not commute. In other words, the order of these operations matters. If you interchange a time scaling and time shifting operation, you will fundamentally change the overall transformation that's being applied. So the order matters. And to make matters even worse, it turns out that the intuition that most people tend to have about the order that these operations are applied in is often backwards from what it really is. In other words, the intuition often is wrong. So let's look at this in more detail. So given that x and y, these 2 functions, are related by this equation here, how can we get from the function x to the function y? So suppose I gave you a graph of the function x and I asked you to find the function y, given that they were related by an equation that looks like this equation here. Well, there's 2 ways that we can go about doing this, both of which are equally valid mathematically. The first approach, which I've labeled by number 1 here, is that we can apply time shifting first. So we take our function x, we apply a time shift by b, and then we take the result that we've just obtained and we time scale it by a factor of a. The other option we have is we can take our function x and we can time scale first. So we first time scale x by a factor of a, and then we take the result we get from that and we time shift it by a factor of b over a. And one thing you'll notice here is the amount that we're shifting by in both of these cases is not the same. In the first case, we're shifting by b. In the second case, we're shifting by b over a. And the reason that they're not the same is because these operations do not commute. So if we interchange the order, which is effectively what we're doing, in the first case we're shifting first and then scaling. In the second case we're scaling first and then shifting. So we've interchanged the order of these operations, but because they don't commute, if we interchange the order in order to keep the overall effect of the combined transformation the same, we have to somehow fudge things to correct for the fact that they don't commute. And this is essentially why these two time shifts are not the same. Here we have a shift by b, and here we have a shift by b over a. Now, to make matters worse, the intuition you might have about the order in which these operations happen may be incorrect. And let me explain this further. So this first approach here, option number 1, essentially comes from just taking the equation from up above and just viewing it directly as it's written. In other words, just viewing it like this. If we view things from this point of view, we know when we subtract a constant b, this corresponds to a shift by b. And we know that when we multiply by a constant a, this corresponds to time scaling by a factor of a. And where the intuition often leads you astray is that a lot of people have the following intuition, which is incorrect, or at least what the intuition leads you to in terms of a conclusion is incorrect. So someone will look at this expression at minus b and say, well, order of operations says that I have to multiply t by a first and then subtract b, because order of operations says you multiply before you add or subtract. And then the next kind of step in the flawed logic is we say that, well, a is associated with time scaling, and because order of operations says we have to multiply the a first, this means that we're time scaling first by a factor of a. But clearly this is not the case, because we're time scaling second. We're actually time shifting first. Okay, so that doesn't look so good. Maybe your intuition might lead you astray in that case in terms of the order in which these operations occur. But let's look at the second case. So this second option, option number 2, it corresponds to taking the equation up above here and just rewriting it slightly differently by doing some basic algebraic manipulation. Essentially what we've done is we've factored out the a here. So we've written this as a and then in brackets times this whole factor, t minus b over a. So in this expression we can see that we're subtracting b over a. So this is what's leading to a time shift by b over a. And we're multiplying by a constant a, so this is going to lead to this scaling by a factor of a. But if we look at the order in which these operations occur, again, something might kind of trouble you a little bit. Your intuition might be kind of nagging at you, saying, I don't really understand why things are the way they are. And in particular, if we look at things more closely, order of operations says that we have to do what's in the most deeply nested brackets first, right? Brackets take priority over everything else. So we have to subtract the b over a first. And because subtracting the b over a is associated with time shifting, our intuition would seem to suggest that this must correspond to a transformation where we're shifting by b over a first and then scaling by a. But this is wrong, because if you look at the order in which these operations are happening in option number 2, we're actually scaling first and then shifting. So like in both of these cases for option number 1 and option number 2, your intuition may lead you astray in terms of if you try to reason about the order in which these operations are happening, you may come to the wrong conclusion about the order in which they're happening. Now I'm going to come back to this later on a subsequent slide to explain where the flaw in the logic is here. There's nothing wrong with order of operations. Order of operations still completely apply, but there's another flaw in our logic which is leading us to the wrong conclusion about the order in which the shifting and scaling operations should be happening. So again, I'll come back to this later because it's extremely important. These types of combined time scaling and time shifting transformations occur all over the place. So if you can't understand what they mean, this will cause you a great deal of grief. At this point, I'd like to go through an example to illustrate combined time scaling and time shifting transformations, and in particular, I'd like to go through example 3.3. In this particular example that we're going to go through, we're essentially going to prove the result that was stated on the slide that we were just looking at a little bit earlier. In particular, we're going to show that if we have two functions that are related by this transformation here, in other words, we have the functions x and y that are related by an equation of this form, where a and b are real constants and a is not equal to 0, that you can obtain the function y by first time shifting the function x by b and then time scaling the result by a. Or alternatively, you can obtain y by first time scaling x by a and then time shifting the result by b over a. So we're actually going to prove that these statements are actually true. And the reason for me to want to go through this particular example is not so much from the point of view of doing a proof to show that the result from the earlier slide is correct, because proofs are not really that fun, and I'm sure that most of you are willing to trust that the results that I'm presenting are correct. But really the reason for wanting to go through this example is to point out some pitfalls and problems that you can run into when you're dealing with time transformed functions. In other words, transformations of the independent variable. So let's do part A first. So we want to show that y can be formed by first shifting x by b and then time scaling the result by a. So what I'm going to do is I'm going to let f denote the result of time shifting x by b. So I'm going to basically shift and then scale. So I'm going to shift first by b. So let the function f denote the function x shifted by b. So by definition, that means that x and f are related in this way. We're basically applying a time shift of b to x in order to get f. And the really important thing that I'm doing here, notice that I'm giving a name to this time transformed function here. Whenever you're dealing with time transform functions, in other words, you've generated some new function by applying a transformation of the independent variable to some other function, always give that new function a name. Otherwise, it gets extremely error prone and very easy to make mistakes when you're trying to manipulate these time transform functions. If you always give the functions a name, it greatly reduces the possibility of making mistakes. So then, according to this rule up above here, after we've shifted our function x by b, it says then we scale the result by a. So I'm going to take my function f, and I'm going to apply a time scaling of a to this function. So that means I take the independent variable t and replace it by at, and I'm going to call this result g. So the claim that's essentially made here is that g should be equal to y, if the claim up above here in part A is true. So let's actually check. Because we know that f is related to x, right? So we can rewrite the right-hand side of this equation here by plugging this equation for f into the right-hand side here. So if we do this, what this gives us is this next line here. We just get that f of at is equal to x of at minus b, which is equal to y of t. So in fact, we did actually get the function that we claimed to get. In other words, we claimed that this whole process would give us the function y, which is equal to x of at minus b, and in fact this is what it gave us. It gave us x of at minus b. So this proves that part A is correct. Now let me just scroll this up here, and then we'll focus on part B. So in part B, we want to show that if we first time scale x by a and then shift the result by b over a, this should give us y. So we just go through a similar process. We're going to start out with our function x, and then we're going to apply time scaling by a factor of a, because this is what the example is saying here. We're going to first scale by x by a. So by definition, this just means we take our independent variable t and replace it by a times t. And the critical thing in this solution is notice that I give a name to this transformed function. I don't just leave it with x of at, I give it a name and I call it f. So the function f is my time-scaled version of x. And then according to this rule up above here, the claim that's being made is that if we take this result that we obtained from scaling and then we shift this result by b over a, this should give us y. So let's try this. So we take our function f and we're going to apply a time shift of b over a to it. So by definition, this means that we're going to take our independent variable t and replace it by t minus b over a. And the critical thing here again is I'm going to give this time transformed function on the right-hand side a name. I'm going to call it g. And the claim that's being made, the thing that we're trying to prove, is that in fact g is equal to y. This should give us the function y. So we can check this, because what we can do is this right-hand side that's expressed in terms of f, we have a formula for f on the previous line, so we can substitute this equation for f in for f here, which is what we're doing on this next line, and simplify. So when we do this, when we plug in the expression for f in terms of x, we get this next line. We can then multiply this a into the quantity in square brackets here, which gives us at minus b. In other words, this right hand side is equal to x of at minus b, which by definition is equal to y of t, because up above here, if I scroll back up, x of at minus b is by definition equal to y of t. So in fact, this process does give us the function y, as is claimed in the problem statement. Again, the main takeaway from this example, really the main example I wanted to go through this, is always get into the habit of whenever you're working with time transformed functions, like for example time shifted functions, time scaled functions, and so on, always give a name to the time transformed version of the function. Like here I gave a name f to this function, here I gave a name g to the function, and then up here in the first part of the example I gave names f and g to these functions here. As long as you do this, you're much less likely to make mistakes and have errors in these types of problems when you're manipulating time transformed functions. On this slide I have an example illustrating a combined time scaling and time shifting transformation. So in this particular example, we're given the function x that's shown in this graph here, and then we're asked to find the function y, where y and x are related by this equation here. So in terms of the equations that we were looking at earlier, this corresponded to the value that we were calling a, and this value here corresponded to the value we're calling b. And we saw that there were two different ways that we could go about solving this problem. One is we can time shift first and then scale. The other approach is we can time scale first and then shift, as long as we're careful about the amount that we're scaling and shifting by. So I'll do the first of these approaches first. So with the first approach, we're going to first time scale by 1, and then time shift by 1, and then time scale by a factor of 2. So if I time shift first by a amount of 1, this is positive 1, so we're going to be shifting in the positive direction, which means we'll shift the graph 1 unit to the right. So going from this graph here to this one here, the graph just shifts 1 unit to the right. Then we have to scale this result by a factor of 2. So time scaling by a factor of 2 will compress the graph horizontally by a factor of 2, which gives us this graph here. So this is the function y. But we have another way that we could do this. We could instead do the time scaling first rather than shifting. So the second approach corresponds to the bottom half of the slide. So we start with this function here, and we're going to first time scale by a factor of 2. So this graph here is going to get compressed by a factor of 2 in the horizontal direction to give us this result. And then we have to take this result and time shift by 1 over 2, because it's b over a. In other words, it's this value here which corresponds to our b value from earlier, and this a value, this corresponds to the a value from earlier, this value 2. So it's b over a, in other words 1 over 2. So if we take this graph here and we time shift by 1 over 2, or 1/2, because it's positive 1/2, the graph is going to shift a half unit to the right in the positive direction, which gives us this graph here. And not surprisingly, we get the same result whether we use the first approach, which gave us this graph, or the second approach, which gave us this graph, because we proved before these two approaches are equivalent. They therefore should give the same result. At this point, I'd just like to make a few additional comments about independent variable transformations. So a transformation of the independent variable can be viewed in two different ways, in other words, viewed from two different points of view or two different perspectives. One is we can ask the question, what effect does a transformation have on a function? But we can also view things from a very different point of view, which is we can consider the effect that the transformation has on the coordinate axis, in other words, on the horizontal axis. And this is an important distinction to make, because the transformation has opposite effects on the function from the horizontal axis. So I'll just try to illustrate this by way of an example. So if we consider a time-shifting transformation where we replace the independent variable t by t minus a constant b, this can be viewed as a transformation that takes our function x and shifts it right by b units. But alternatively, there's a different perspective that we can take, which is we can view things from the point of view of what the transformation does to the coordinate axis. And you can show that this type of transformation will shift the coordinate axis, in other words the horizontal axis, left by b units. Notice that the direction in which things are shifting is different here. We have shifting right when we interpret things in terms of what is happening to the function, and we have a shift in the leftward direction in the case that we consider what effect the transformation has on the coordinate axis. Now in engineering, really all we care about when we're dealing with independent variable transformations is the effect that the transformation has on the function. We don't typically care about what the effect is on the coordinate axes. And the reason for this is simply that coordinate axes are not very interesting. They're just lines. On the other hand, the function represents the data that we're dealing with to solve some kind of engineering problem. So for this reason we take on a very function-centric point of view. We care a great deal about what these transformations do to functions, but we don't really care too much about what's happening from the point of view of the coordinate axes. And we have to be very careful to keep this in mind because we always want to be taking the perspective of what's happening to the function, what's the effect of these transformations on the function. We want to make sure that we don't accidentally interpret things from the other point of view, which is not the point of view that we care about. Otherwise we'll probably get quite confused and end up with a lot of contradictory results. At this point I'd like to do a short demo to illustrate the two different perspectives from which you can view an independent variable transformation. Okay, so what I have here is just a simple demo to illustrate the different perspectives from which you can view an independent variable transformation. So the particular type of transformation I'm going to consider is a translation or a time shift. So what I have here is just a graph of a function which is just a triangular pulse, a very simple function. And what I'm going to do is I'm going to apply a translation or a time shift to it. And just to make this a little bit easier to animate, I'm just going to take this other piece of paper and put it over top of the first one, and just it essentially has the same graph plotted on it. So what I'm going to do is I'm going to start shifting the axes to the left very slowly. And as I'm shifting the axes to the left, well, obviously the axes are moving leftward with respect to where they were originally. But as I'm moving the axes leftward, what I want you to consider is which direction is the function moving with respect to where it was originally. You can see that as I'm moving the axes leftward, in other words, the axis is moving left relative to where it was originally, the function is actually moving rightward relative to where it was originally. So the main idea I'm trying to convey here is that there's two different perspectives from which you can view an independent variable transform. In this case we're talking about a translation or time shift type of transformation. And depending on whether you view things from the point of view of what's happening to the function or what's happening to the axes, the direction in which the shifting happens is opposite. In the case of the function it's shifting one way, in the case of the axes it's shifting in the opposite way. And it's a similar sort of effect for other types of time transformations as well, like for example time scaling. But time scaling I can't really do it very easily in terms of a demo because I would need some kind of elastic sheet of paper that can stretch and so on, which unfortunately I don't have. But anyway, I hope this kind of conveys the basic idea that there's two different perspectives that you can view an independent variable transformation from. You can ask the question, what effect does it have on the axes? Or you can ask the question, what effect does it have on the function? And the effects are opposite of one another. Now that we've spent quite a lot of time talking about independent variable transformations, I'm going to switch topics and talk about dependent variable transformations. So the first type of dependent variable transformation that I'd like to introduce is what's known as amplitude scaling. So an amplitude scaling transformation maps a function x to the function y, where x and y are related by an equation of this form, where the constant a is a real number. So all we're effectively doing in this type of transformation is just multiplying our original function by a constant. Geometrically, in terms of the effect this has on the graph of the function, is it affects the vertical scale of the graph. It can either expand or compress the function vertically, and also it may reflect the function as well if the scale factor is negative. So just as an example, in the top left graph appearing on this slide, I have a function x, and then the three remaining graphs on the slide are just various different amplitude scaled versions of x. So in this case, we're multiplying x by a factor of 2. So you can see the graph gets stretched vertically by or the function gets stretched vertically by a factor of 2 in this graph compared to the original graph of x. In this graph here in the bottom left, where we have 1/2 x, x has been scaled by a factor of 1/2, or equivalently divided by 2. And the effect this has on the graph is it essentially compresses the function in the vertical direction by a factor of 2. And then the last graph that we have in the bottom right, we've multiplied x by a factor of -2. Because -2 is a negative value, the graph flips upside down, so it's inverted. But in addition to this, because of the 2 that we're multiplying by, this part, we also get a stretching effect. The function gets stretched vertically by a factor of 2. The next type of dependent variable transformation that I'd like to consider is what is known as amplitude shifting. So an amplitude shifting transformation maps a function x to a function y as given by the relationship here, where b is a real constant. So effectively all this transformation does is just add a constant to a function. And geometrically the effect that this has on the graph of the function is it just vertically displaces the graph either upwards or downwards. So for example, if we have a function x like what's shown in the graph on the left of this slide, if we then subtract 2 from the function x, the effect that this has is it vertically displaces the graph of the original function x, moving the function downwards by 2 units. The last type of dependent variable transformation that I'd like to introduce is simply a combination of amplitude scaling and amplitude shifting. So for example, we can have a transformation that maps a function x to a function y according to an equation of this form, where a and b are real constants. So all we're doing is we're just taking our function x and we're scaling it by a constant a, and then we're also adding b to the result. This transformation, of course, can be rewritten in the form that's shown just below here. Essentially all we've done is we've just factored the a out front of the rest of the expression, but clearly these two expressions are equal. And these two ways of writing the same equation correspond to these two different interpretations. This basically corresponds to, this way of writing things corresponds to first taking our function x and amplitude scaling by a. In other words, this part here, we're first amplitude scaling by a, and then we take the result that we obtain and we amplitude shift by b, which is the last part here. Alternatively, we can write things in this way because this equation is equivalent to the one above, but this leads to kind of a different way to interpret the same operation, which is that because of order operations, we have to first do what's in the brackets here. So we're first going to be applying a amplitude shifting by b over a, and then we take the result of that and we amplitude scale by a factor of a. So this is basically this case here. But unlike the case of independent variable transformations, this tends to align very well with people's intuition. So dependent variable transformations tend not to cause so many problems and difficulties for students, whereas independent variable transformations are often much more problematic.